All right, let's look at another example. This is going to be an implicit example. And I think it's important to look at implicit examples because as you go forward in math, depending on what kind of math you do, but most likely the relations you get will be more and more implicit. And so what do I mean by that? Well, we're just going to be looking at the sphere. Let's look at the sphere with radius 2, so x squared plus y squared plus z squared equals 4. And I'm not going to get this into a z equals format, because if I did, it would be a root, and then I would only be having half the sphere. And if you put a plus or minus, that like kind of fixes it, but that's not really a function anymore. So that's not as good. So if you can, avoid taking roots, avoid dividing by variables, avoid taking inverses, trig inverse functions. Those can mess with your domain. Sometimes logs too. So if you can just work with this implicitly, that's the best. Okay, and we're going to be examining this at 2 points. We're going to be 1, 1, and actually if I give you 1, 1, you should be able to find the z coordinate, right? 1, 1, root 2, and 1, 1, negative root 2 are the two possible z coordinates. Let's just make a little sketch here. So we make x, y, z, and then we should be able to get a sphere, radius 2, and then where is this point? 1, 1, root 2. So not completely to the edge of the sphere. I don't know if you can tell where that is. So there's 1, 1, root 2, and 1, 1, negative root 2 are those two red dots. Okay, good enough for a sketch. Okay, let's take the derivative of this implicitly. So first we'll take partial derivative with respect to x. So what happens there? We get 2x, y is a constant, so derivative of y squared is 0, and then z does depend on x, so we're going to write 2z times the partial derivative of z with respect to x equals, and then derivative of 4 is 0. So I can solve for zx is negative x over z. And that's a lot cleaner than writing z as a root anyways. You would get the same answer, and like, yeah, okay, that has a z in the answer, but I'm not worried. I'm just going to leave it like that. And then if I do the same for y, partial derivative with respect to y, I should get negative y over z, right? It's completely symmetrical, but let's do it just in case. So derivative of x squared is 0 because x is a constant with respect to y if we're taking the partial. Partial derivative of y squared with respect to y is 2y, and then partial derivative of z squared is 2z times the partial of z with respect to y, and then derivative of 4 is 0. So we're doing chain rule there. And then zy, this is one-dimensional chain rule, not the chain rule we just learned, is negative y, not over x, over z. Okay. Great, so then we can actually write the gradient. Del of z is, we can just leave it like this, negative x over z, comma negative y over z, unless it specifically says write it in terms of x and y. No reason why we can't leave it like this. Okay, so then at the point 1, 1, root 2, del of z is going to be, and I'm just going to put in these values for x, y, and z. So negative 1 over root 2, comma negative 1 over root 2. Let's see if we believe that. So if we walk to that point, 1, 1, root 2. If I walk, this basically says in the x direction, I'm going down at a rate of negative 1 over root 2. This is about negative 0.7, in case you're curious about how big that is. And then if I go in the y direction, it is completely symmetrical because this is on the plane y equals x. Then I'm also going down about negative 0.7. Okay, and then the magic of leaving it in terms of x, y, and z is if I put in 1, 1, negative root 2, then my del of z, I'm putting in a negative root 2 for z, so we have two negatives which make a positive, so that's positive 1 over root 2, comma positive 1 over root 2. And what does that say? Well, that's exactly what we expect. If we go down here and walk in the x direction, now we're going up, and we walk in the y direction, we're also going up. Okay, so that's good. Our del takes care of signs for us, as long as we're not too sloppy. Okay, that's great. Let's look at directional derivatives now. So let's see, let's go back to, let's do this in general. So the directional derivative, we'll go back to our general definition, or our general format for del of z, and then we're going to do the directional derivative of 1 comma 0, this is just a sanity check, of z is del of z dotted with the vector 1 comma 0, right? And so that's negative x over z. Okay, that's great. That equals partial derivative of z with respect to x. And then del of 0 comma 1 of z, or directional derivative of 0 comma 1 in the direction 0 comma 1 of z is del of z dotted with 0 comma 1, which is negative y over z, which is zy. Okay, that's good. Those are by definition. Now, let's look at directional derivative of 3/5 comma 4/5 of the function z at the point 1 comma 1 comma root 2. Okay, so actually I can use this pre-evaluated del of z at 1 comma 1 comma root 2, so negative 1 over root 2 comma negative 1 over root 2 dotted with 3/5 comma 4/5. And I'm just going to get a total of negative 7/5, and there's a root 2 in the bottom. Okay, so what does that mean? That means if I start at this point, 1 comma 1 comma root 2, let's maybe use a different color, and then I walk in the direction 3/5, 4/5, so more in the y than the x, then I end up going down, right? And then how far down? Well, that far down. That's about, what, 1.4 times 0.7? Okay, I can't do that. It's close to 1. It's close to negative 1. So, cool. Is that right? That might not be right. I think that is right. Close to negative 1. Let's see. Yeah, very close to negative 1. Okay, and then what does this mean? If I go to that point, 1 comma 1 comma root 2, what's the direction I walk in for maximum positive steepness? I have to walk in the same direction as the del. It turns out this is actually a unit vector. You can check that. So walk in the direction 1 over root 2, comma 1 over root 2. And then for maximum negative steepness, I walk in the other direction, the opposite direction, negative 1 over root 2, negative 1 over root 2. So let's see what's happening on the sphere. If I walk in basically the same direction in the x and the y, I go either down really quickly or up really quickly. And then 0 steepness, I'm going to be orthogonal to this, so I need 1 positive, 1 negative. And you can make this a unit vector or not. What if I just didn't and I just walked in the direction 1 comma negative 1? Let's just look at what that is. If I walk in the direction 1 comma negative 1, so I'm going positive in the x, negative in the y. I'm going this way. And what ends up happening, this is actually the tangent vector to this level curve of the sphere, which is a circle. So that's what I'm finding there with these vectors that are parallel, basically, and orthogonal to the gradient vector.